Hello. How are things going? Rather quiet today. Wait for a minute or so for people to join. All right. It is 11 a.m. So uh, well, let's do a brief review of what we did last time. Everyone hear me? Yes. No.
Yes.
Okay. All right. So last time we talked about the augmented Lagrangian method, right? So and the idea was that if we add, oh, this, yeah. Wait a minute. Thought this is not the beginning of the lecture, is it? Okay. Yeah, that's. I don't know what happened there. Okay. All right. So yeah, so the augment. So we said that if we look at the penalty method, that's used that can be used to solve equality constraint problems, then of course you need to let this penalty go to infinity with iterations as k goes to infinity. And if that happens, it could cause some problems with conditioning. In other words, as ck becomes large, the unconstrained problem that's obtained using the penalty function may become harder and harder to solve. Okay, so the convergence might be quite slow. So one way around that, I said, was to add another term to this Lagrangian, to this augmented Lagrangian, and well, add another term to the penalized function, essentially, which is the Lagrangian term lambda transpose h. And adding this lambda transpose h actually turns out to have some nice advantages, especially if you can choose this lambda close to lambda star, which corresponds to the global minimum of the original optimization problem, right? And if we can do that, then we don't need to let ck become that large in order to get close to the optimal solution using this method. Okay, so that's good. That's good to know. But how do we make that happen? How do we make lambda close to lambda star? And that's we exploited duality to do that. Okay, and we basically showed that you know, the optimization, the lambda star is actually essentially going to be the maximum of the dual function. And so if you can find the gradient of the dual function, you can use gradient descent to find lambda star. And then we said, well, if the d lambda is differentiable, then the gradient of d lambda just happens to just equal h of x lambda. Okay, so you can do gradient descent to find lambda star from d lambda using an iteration like this, basically alpha k times h of x lambda k. Okay, and today's class we'll see that even if when gradients don't exist, okay, and in fact actually you see it more, it'll be in the homework, even when gradients don't exist, that this h of x lambda will basically play the role of a gradient. Okay, so it's to be a subgradient essentially for this problem. And so and this led to this method of multipliers where you minimize this augmented Lagrangian over x, but in each iteration you also update your lambda using this gradient ascent step. And this gradient ascent step should basically take you towards lambda star. So as k becomes larger, you're approaching lambda star. So you don't need to make ck become very large in order to get a good solution. And this is exactly what you're going to verify in computer assignment 3. Okay. So any questions about the method of multipliers? Okay. We're going to be changing gears today, and we'll talk about subgradient methods. So that's the topic. In fact, this is the last topic that we're going to do before your midterm. And it's also something that will be covered in your homework, latest homework assignment. All right. So we talked about gradient descent methods a lot earlier in the course. And all gradient descent methods require the gradient to exist, of course, right? If the gradient doesn't exist, you can't apply the method. So, but there could be interesting optimization examples for which the gradient doesn't exist at some points. It may exist at most points, but there may be places at which the gradient doesn't exist. So if the gradient doesn't exist, then now let's recall what happens if the gradient exists and f is convex. Suppose f is convex. For now, let's not constrain anything, because you can always add a domain constraint to all these things, but it just gets a little messy to keep track of it all over the place. That's as we did before earlier in the course. When we talk about unconstrained optimization, we'll assume that f is defined over the entire space Rn. Okay, and if there are special cases when you take logs and so on, we'll deal with those special cases on a case-by-case basis. Okay, so if f is convex on Rn, then we know that fy is going to, it's basically the function is lower bounded by the first order Taylor series expansion, right? So if you look at the first order Taylor series expansion, which is the gradient transpose y minus x plus fx. So this fy is lower bounded by that, right? We know that. Okay, so we're going to use this kind of this property of convex functions to define something called a subgradient. Again, we define a subgradient. Subgradients can only be defined for at all points for convex functions. So, and of course, if the function is not convex, if it's concave, we just take the negative and you get a convex function, and you can again define subgradients. Okay, but if it's neither convex nor concave, then we'll talk about that in just a minute. But you may not have subgradients. So our definition of subgradients will be restricted to convex functions. Okay. So for a convex function on Rn, g is called a subgradient of f at a point x in Rn if this convexity property holds with the gradient replaced by g. Okay. So, but of course, a subgradient need not be unique. All right, that's why I said g is called a subgradient of f at the point x if this condition holds. Okay. Now, let's look at some properties of this subgradient, and then we'll do examples to make this all more clear. So, a property of subgradient is that the subgradient always exists at any point for convex functions. The proof of this gets a little technical because it involves something called it involves the separating hyperplane theorem for convex sets, which there is a proof, short proof of that given in the appendix, so you can look that up. But you can believe. I will actually look at what a subgradient is an example. Then you should believe that the function is convex. You can always find such at any point you can always find a G that satisfies that property. Okay. Now, if the gradient exists at some point for a convex F, then the subgradient is unique. There's only one subgradient for that point, and it equals the gradient. Okay, so gradient exists, then subgradient is the same as the gradient. Right? Now you could think of carrying over this definition of subgradient to non-convex F. You can do that, but the subgradient need not exist. And actually, it's not hard to see why the subgradient may not exist, because if you have non-convex F, even if the gradient existed, this condition may not hold, right? At all points, right? So the function is not going to be lower bounded by the first order Taylor series expansion. So if it doesn't hold even when the gradient exists, then that's a special case of a subgradient, and so this may not hold. So it may not exist. So that's why we don't bother with defining subgradient for non-convex functions. Okay, any questions so far about the definition? All right, so let's do an example that should make things a little more clear. So the example is just the modulus function, absolute value of x. Okay, so one-dimensional, simple example. And so we have this function, and you can see that for any x that's not equal to 0 here or here, the gradient exists, and so the gradient will be the same as a subgradient. If the gradient exists, then and the function is convex, then it automatically satisfies the property of the subgradient, so you don't need to check it. Okay, you get that directly from convexity, like we proved in whatever lecture that was, where we proved that lecture 4 maybe. Yeah. Okay. So the only point that we have to worry about is this point 0, the origin. And there you can see that I've drawn two green lines here. Okay, and they're both both of these lines, okay, underestimate this convex function. Right? They're tangential here, and they both underestimate this convex function. In fact, any line that basically is parallel to this 45-degree line here, slope 1, between that and all the way up to here, all of those lines lower bound this convex function, right? Which means that basically any G in the set -1 to 1 should be a subgradient at 0. Any slope between -1 and 1 is a line with any of those slopes will lower bound the convex function. So any G in the set -1 and 1 is a subgradient. Okay, Now we can prove it formally by just to prove that something is a subgradient, you need to show that this condition is satisfied, this condition. Okay, that's how you prove that something is subgradient. Okay, so there are 3 homework problems that you have in the latest homework where you're asked to find subgradients, and all those 3 examples, you basically have to verify this condition to show that it's subgradient. Okay, all right. So let's actually quickly mathematically prove this. I mean, by picture, we already see that it's true. We can also show it mathematically by just look. So f of y is just the absolute value of y. So for y positive, you have to consider 2 cases just to make things simple. So for y positive, f of y is the same as y. And this is bigger than f of 0, which is 0, plus any g times y. This will hold for all g belonging to -1, 1, right? Because y is positive, okay? Y is positive on both sides. And as long as g is bounded by an absolute value by 1, y will be bigger than gy. Right? So this condition does hold. This lower bound condition does hold for y positive. Now let's see what happens when y is negative. When y is negative, then f of y is minus y, which is a positive number, right? And in this case also, it's easy to see that this is f0 plus g of y. So minus y will be bigger than g of y for all g belonging to -1, 1. Because at most, what can happen on the right-hand side is that you multiply by -1. In that case, both the left-hand side and right-hand side are equal. And for any g that's between -1 and 1, the right-hand side will be smaller. Okay. So this is basically another way of seeing exactly what we saw in this picture, which is that all of these lines form subgradients for this function at 0. So is the definition a little more clear now of subgradient? Okay, so now let's give another definition. So since subgradients are not unique, the set of all subgradients at a point x is called the subdifferential, which is actually a set in general. So it's called a subdifferential at x, denoted by this del operator, del of x. Okay. I know we also use the del operator for partials, but that's the symbol that's used for a subdifferential as well. Hopefully, it'll not cause any confusion as long as you use it in the right context. So for the example we had above, what that says is that subdifferential for all points that are negative, all x's that are negative is -1. Subdifferential at all points that are positive is +1. And at 0, the subdifferential is this entire set from -1 to 1. Okay, so the subdifferential is -1 if x is negative. It's a set -1, 1 if x is equal to 0, and it's 1 if x is positive. Any questions? So remember, the subdifferential is not a function because it maps one value of x to multiple values, right? In this case, a set. So don't think of it as a function. So some people will think of this as a sine function, but it's not really a sine function because at x equal to 0, I have multiple values that this function takes, right? That it would take, so it's not a function. All right. Any questions? Clear? Looks like somebody, Chelsea, you unmuted. So do you have a question? Okay. All right. So let's look at some basic properties of this subdifferential. And you're going to prove these in your homework. It's just very short proofs. It's easy to do. Just you have to verify that the definition of a subdifferential holds. So if you scale f, then the subdifferential gets scaled by something positive, of course. It has to be positive because if you scale by something negative, the function convex function will become concave. So again, you stub the subgradient won't even be defined, right? So that's why it's scaling when they're positive. If you add two convex functions and take their subdifferential, you get the sum of their subdifferentials. Again, it just follows from the definition of a subgradient. And then here's something that's a little more interesting. So if you do an affine combination, so you take X and multiply by some matrix A and add B, and it doesn't have to be a square matrix, then the subdifferential of this function that you form, by the way, if f is convex and you're taking, it's a composition of a convex function and a linear function, will still remain convex. So h will still be convex, so you can define its subdifferential, and the subdifferential of h is given by this expression. You're going to prove this in your homework as well. Okay. So if you're trying to find subdifferentials for certain functions, if they are a little complicated, you can break things up a little bit and find subdifferentials of components and then put things back together using these properties. Okay. All right, let's do another example. Unless you have any questions. Okay, so let's look at this function. This actually is a function that I got from example. I got from the exam the practice exam that I posted on the website for you guys to prepare for exam 2. And but there was a bit of there's some errors in the solution, just like with the first practice exam that I put up. I just had the PDF files that Professor Srikanth gave me, so I couldn't easily correct them. But you for this example, we'll actually go over the solution. They're basically minor typos, nothing more than that. But I think there were some questions about it on Piazza. So let's see. So this example. We have the function is the max of 1 and absolute value of x minus 1. Okay. Now this is a convex function. And why is it a convex function? Because if you look at the components that make up this max, we have f1 of x equal to 1, and f2 of x is absolute value of x minus 1. Both of these are convex functions, and you take the max of two convex functions, you get a convex function. Okay, we know that. So, and you can actually plot this and see that it actually is a convex function. It's one-dimensional, so you can do that. But in higher dimensions, of course, it's useful to be able to use properties like the max of a bunch of functions is convex functions is convex, and so on. So we have this function that looks like this. Okay, so from -2 to 2, it's this flat version, and beyond 2, it has a slope of 1, and before -2, the slope of -1. Okay, so if you were so the way you typically do it to find subgradients is to essentially guess it first. Okay, in many examples, that's the easiest way to find subdifferentials. And you can make a good guess based on the form of the function, In this case, we actually plot the function, and then make it easy to guess. And then once you have that guess, then you can verify that it's true by checking the definition. Okay, so what should our guess be for these subdifferential of this function f? So from minus infinity up to the point -2, what should it be? All the way up to here.
-1.
-1. And between -2 and 2, it's 0. The gradient exists and it's equal to 0. Above 2, the gradient exists and equal 1, so it has to be 1. But so the only points at which you have non-unique subgradients is at -2 and +2. Okay, and at -2 and +2, from this plot, you can see that the subgradient at +2 should go all the way from 0 to 1, and the subdifferential at -2 goes from -1 to 0. All right, so let's write down our guess now. Right, so this is -1 if x is less than -2. It's the set from -1 to 0 if x is equal to -2. It's 0 if -2 less than x less than 2. 0, 1 if x equals 2, and 1 if x is bigger than 2. Right? Is that good? All right. So now let's actually show that this is the case. Right? So we need to prove this. We need to prove that the subdifferential is given by this set here. Now, of course, at any point where the gradient exists, so basically for all x except for x equal to x equal to -2 and x equal to +2. So we can apply the result from lecture 4 for convex functions, and we know that since the function is convex, that this holds. At those points, the subdifferential is unique, and it's the same as the gradient. So basically, we only have to worry about these 2 points, x equal to 2 and x equal to -2. Okay, so let's look at the point x equal to 2. What do we need to show there? So at a point x equal to 2, we need to show that fy is bigger than the f at 2, fx, which is f at 2, which is actually equal to 1, right? Plus g times y minus 2, the subgradient times y minus 2. And this has to hold for all g belonging to 0, 1, because we're trying to show that at y equal to 2, at x equal to 2, that the entire set from 0 to 1 are candidates for subgradient. Okay. So here again, it's useful to separate out cases and prove that we need to prove this condition. So we'll prove it for 2 different cases on y, just to make things easier. Okay. And I think this is where there was a small typo in the solutions for the exam on the website. Okay, so let's look at the case when the absolute value of y is less than 2. And then we know from this function that in this range from -2 to 2, the function is basically equal to 1. So f of y is equal to 1. And so we need to show that f of y, which is 1, is bigger than f of 2, which is 1, plus gy minus 2 for all g in 0, 1. We need to show this. But that's the same as showing that g times y minus 2 is less than or equal to 0 for all g in 0, 1. Right? But if you look at y minus 2, this thing, the absolute value of y is less than 2. So this is always less than 0. So for any g in 0, 1, the g times y minus 2 has to be less than or equal to 0. At best, it can be 0, but otherwise it will be negative. Right? So this is true. So we verified this condition. We verified this condition when absolute value of y is less than 2. So now let's look at the other case, if y is bigger than 2. So if y is bigger than 2, then the max of 1, y minus 1, is the same as y minus 1, because that second term dominates the max. So what we need to show now is that y minus 1 y minus 1 is bigger than 1, which is f2, plus gy minus 2 for all g belonging to 0, 1. Right? Okay. So this is the same as showing that absolute value of y minus 2 is bigger than gy minus 2. But since absolute value of y is bigger than 2, that implies that y minus 2 is bigger than 0. And so for all g belonging to 0, 1, sorry, a cat just came in here. Hold on. All right. So y is bigger than 2 means that y minus 2 is positive. And so if you look at any g in the set 0, 1, g times y minus 2, right, is less than or equal to g times the absolute value of y minus 2, that of course holds, which is going to be less than, since g is between 0 and 1, this is less than or equal to y minus, absolute value of y minus 2. Okay. So if we call this condition that we need to prove star, we've just established star. Okay. So this means that we have shown that the differential of f at 2 is equal to the set 0, 1. And you can similarly show that the differential of f at minus 2 is minus 1, 0. Okay. Same steps to show that. All right. Any questions?
Why does g y minus 2 smaller equal to g absolute y minus 2 smaller or equal to
because absolute value of y is bigger than 2. Okay. So that will have to hold. Because what can happen? The only thing, so if y is actually bigger than 2, that obviously holds. If y is less than 2, then the left-hand side is negative, basically. So it'll still hold.
And what about g absolute y minus 2 smaller than absolute y minus 2?
Yeah, because G is between 0 and 1. Okay? So multiplying something that's positive by something between 0 and 1, it'll just make it smaller.
Oh, so G is like G is a number, not a function.
No, G is some number between 0 and 1. Yeah.
Okay, I see. Thank you.
Yeah.
Do we have to prove the other direction? So I think we only showed if G belongs to this interval, then this inequality satisfy.
Yeah, that's all we need to show that G is a subgradient. You want to establish that any value of G between 0 and 1 is a subgradient. In order to prove that, you need to establish that this condition is satisfied, basically.
Yeah, I mean, is it possible like we may have a bigger interval that could be the subgradient?
It's possible that we haven't covered everything in there. Then you have to, yeah. I suppose technically you have to show that no other G's will necessarily satisfy this for all Y. But that's not that hard to see. I guess you can basically go both ways with these implications. If G outside the set, then you won't be able to establish this for all Y. Yeah.
Okay. So like if in high dimensional case, do we always have this sort of property where like the gradient, the gradient discontinue, and we have those subgrading in like those intervals from the two discontinued values?
I didn't quite get your question. So you're saying that if the function is not continuous?
No, the gradient is not continuous. Like in this case, the gradient jumped from 0 to 1.
Yeah, but actually gradient doesn't even exist here, right?
Yes. So like in other case, do we generally have like the subgradient being inside this interval of the two boundaries of?
Yeah. So actually, you'll do one of the examples in your homework is a two-dimensional example. Yeah. So you basically have some region in two-dimensional space that will define the sub differential.
Okay. Yeah. Thank you.
Yeah. Good point. Any other questions? Yeah, well, once you start working with these subgradients, it's really not that hard of a concept. So, yeah, I mean, it's let's actually look at say this example, and so say if instead of this function, or maybe let's go to this example. And so this function just doing this, if it had gone down here, for example, if it had done this, okay, right? It went up and went down. So now this is not a convex function anymore. And then if you try and define a subdifferential here at this point, then yeah, so it depends, you know. So there may be some points for which you can define a subdifferential, for example, or maybe you could do this and then go up here and then go back up or something like that, right? So then I can define subdifferentials here at this point, because I have now made sure that all these guys, for all these lines, my function is above those lines. Okay, but of course I couldn't define a subdifferential here, for example, right? In this case, what would happen is if I tried to define a subdifferential at this point, then I'm drawing a line like this. This might work, keep it above, but then this one may not work anymore, right? And in fact, if this function went down even more, then you know, none of these lines would lower bound the function anymore. Right? So if the function is not convex, you can't really guarantee that a subgradient will exist at all points. Okay, the function is convex. You can see here, at least through these examples, you have some intuition of why, even if the derivative a gradient doesn't exist, subgradients can exist. Okay. Okay, so why are subgradients important? That's what we're going to talk about next. They're important for optimization because there are lots of optimization examples for which the function might be convex but not differentiable. Okay, and you'd still like to be able to apply something like gradient descent in those situations, and you know, and actually a common example these days of functions which are not differentiable might come from something like neural networks, and we saw examples when we talked about neural networks of these activation functions which are not differentiable. So, right? The ReLU function, if you remember, was not differentiable. Okay, it's convex, but it's not differentiable. So you would like to apply gradient methods for those kinds of problems, and so that's where subgradients will play a role. Okay, so it's about 11:40 right now, so time to take a short break, and then after the break we'll talk about how we use subgradients for optimization. All right, any questions?
I have a question.
Mm-hmm.
It seemed like to determine the subgradient at the point where the gradient doesn't exist.
Yeah.
At least in the 1D case, it would work if we just look slightly left and find the gradient there, and to the slightly right, find the gradient there, and set the subgradient to be all the values in between those two
yes
gradients. Like, would it also work in multiple dimensions, like higher
no,
dimensions?
it can get a little more complicated than that. So, and you'll see an example in 2 dimensions and in your homework, right? So it can get a little more complicated than that. But basically, that's the right that's the right intuition, though.
Okay, thank you.
All right. So let's take a short break, and then we'll come back and talk about it. looks like we lost my iPad connection. Okay. Okay, so let's see. Actually, yeah. So who was it brought up the point about the G outside the set? Technically, yeah. I guess I'm thinking about it. You should really be making sure that when G is outside the set that you're saying is the subdifferential, that the condition doesn't hold. But here you can easily check that. If, for example, if G is negative, then this condition will not hold, and if G is bigger than 1, then the other condition for Y less than 2 will not hold. Sorry, no, it's not where else. G is bigger than 1, then this condition will not hold. Sorry, and if G is less than 0, then this condition will not hold. So, so it's easy to verify that when you're outside the set, but technically you should be doing that. But okay, so if you have a problem in the homework or the exam, don't worry so much about that. Okay, because it should be pretty easy to see that the implication goes both ways on the set of values that G takes. All right. Let's look at first order necessary conditions for optimality in terms of subgradients. Okay, so then we can apply subgradients for something like gradient descent. Right? Okay, so the result says, it's a very easy result to prove, and it's basically a minor extension of what you saw in the case where gradients exist. So what this says is that if F is convex and X star is a minimizer of F, then at the point X star, if I look at the subdifferential, that subdifferential must include 0. So 0 must belong to the subdifferential. At X star. Of course, if gradients exist, then the subdifferential is unique, and that's the same as saying the gradient is 0. Okay. All right. So this is actually, the proof is same set of lines as the proof for convex functions, that the minimum at satisfies gradient equal to 0. Okay, so if X star is a minimizer of F, then F at X star must be less than F of Y for all Y belonging to Rn. And then on the left-hand side, what I can do is I can simply add 0 of the vector 0. This is the vector 0. Could be n-dimensional, right? So 0 transpose Y minus X. I've not changed anything on the left-hand side by doing that. And that's less than F of Y for all Y belonging to Rn, right? This means that, of course, 0 satisfies the condition for being a subgradient at X star. This should be an X star. So 0 must be part of the subdifferential at X star. So if x star is a minimizer of a convex function, which may not be differentiable, in particular, may not be differentiable at x star, but 0 has to be within the set, subdifferential set at x star. Okay, so this is good to know. So you can still, basically, this implies that you should be able to use something like gradient descent to find the minimum. Okay, so let's actually try to do something called subgradient descent. And first we'll look at the case of unconstrained optimization. Right. So we assume that f is convex on Rn, right? And we assume that f star, which is the minimum of f where Rn exists, and that there is actually an x star that achieves that minimum. So the infimum exists, and there exists an x star that achieves that minimum, and we'll call that minimum value f star and the minimizer x star. Okay. So, and this is similar to what we did in lecture 6, which I have here. So if you remember this, what was it, lecture 6? Yeah. So this is convergence of steepest descent with fixed step size. And if you remember, we assumed that the f is lower bounded by f minimum, and then we said that, of course, in this case, we didn't use convexity in lecture 6. It was lecture 7 that we used convexity. So that's here, I guess. Yeah. So yeah, f is a convex function that exists x star such that this holds. And then we showed that gradient descent actually converges to that x star at rate 1 over k. Right? Okay, so we're actually going to use very similar ideas to develop a gradient descent algorithm with subgradients. Okay, and so rather than using some kind of Lipschitz condition on gradients, which we can't do because we don't even have an existence of gradients, right? So what we'll assume instead is that the gradient is bounded. Sorry, the subgradients are bounded. So for all x and for all g belonging to the subdifferential at x, the norm of g is upper bounded by some number a, positive. Okay. So if this condition holds on the subgradients, what does it say about the function? So if you remember, we saw earlier that if the gradient is bounded, when gradients exist, then the function is Lipschitz. And here, the gradient doesn't exist, but the subgradients are uniformly bounded. The subgradients being uniformly bounded, you can show that subgradients being uniformly bounded also implies that the function is Lipschitz. Okay, so a lot of these convergence results for functions that are not differentiable assume that the functions are Lipschitz. Okay. All right. So now let's look at subgradient descent with constant step size. So, but the iteration looks very similar to gradient descent, right? But we, instead of using the gradient, we use any gk. We'll use any gk that is a subgradient at xk. So gk belongs to the subgradient set at xk. Okay, so that's our gradient descent. Okay, we don't. how should you pick the one gradient in that set? Gets into finer details. Okay, right now we're going to assume we pick that GK arbitrarily in the subdifferential set at xk. Okay, so what happens if we use this procedure? Okay, can we show that such a gradient descent procedure, subgradient descent procedure rather, converges? And what does it converge to? Right. So we're interested in convergence to x star. So let's look at expanding out xk plus 1 minus x star in terms of xk minus x star. And this is actually identical to what we did here, right? When they go back to lecture 7, and this is exactly what we did. We said, let's look at xk plus 1 minus x star, expand it out. Okay, so this step will be the same, except instead of gradient, we'll have the subgradient here. Right. So okay. Okay. So this is less than, since the GK is bounded by A. So this is xk minus x star squared plus, it's upper bound by alpha squared A squared minus 2 alpha GK transpose xk minus x star. Okay. Now, by definition of GK, we know that since it's subgradient, it satisfies the subgradient condition. In other words, the function at x star is lower bounded by the first order, sorry, not this line, essentially. So f of x star is lower bounded by f of xk plus g transpose x star minus xk. So this g transpose x star minus xk is the same as the negative. So I can make this negative xk minus x star. Now you'll see that basically what this is saying is that this negative of gk transpose xk minus x star is just basically comes from here, and that's upper bounded by f star minus f of xk. So let's put that into that expression up there, and we get that the left-hand side there is upper bounded by xk minus x star squared plus alpha squared a squared plus alpha times, 2 alpha times f star minus f of xk. Is that clear? Okay. So let's see what happens next. What happens next is actually very similar to what we did in lecture 7. So what we did in lecture 7, if you remember, we had this upper bound, then we used this telescopic sum, okay, to get rid of all but the first and the last term, and by summing on the left-hand side. So we'll do something very similar here too. Okay. So what we first do is take this stuff to the left-hand side and write this as xk minus x star squared minus xk plus 1 minus x star squared, and then plus alpha squared a squared divided by 2 alpha. Okay. So now this is where the proof that we did in lecture 7 diverges a little. And the reason why it diverges is because we don't have gradient descent, and so in gradient descent we know that if we choose our alpha small enough, a constant step size, as long as the function is as bounded is gradient as Lipschitz, then if you choose alpha, small enough relative to that Lipschitz parameter, then we saw that you would always decrease the function, right? All right, but that's not guaranteed when you do subgradients, okay? Because you're choosing some number within the subgradient set, okay? So what we'll do, the slight divergence from this step in lecture 7, where we basically had f of the last one, the last step, f of xn is less than f of xk for all these, for all previous values of k. We don't have that condition anymore. So instead of using something like this in today's proof, what we're going to do is define a quantity which is the minimum of all the f values that I've seen up to this point. Okay, and one of these x's will correspond to that minimum, and I'll call that xn star. So xn star is the value of x, among all the values of x that I've seen in the past up to time n minus 1, and the one that minimizes. It results that gives the smallest value for f. Okay, so that's my f of xn star. So now, if I look at, I'd like to sum this guy. I'd like to sum this guy on both sides, because on the right-hand side, that gives me a telescopic sum, and it only keeps the first and last terms, right? When I do the telescopic sum. On the left-hand side, if I sum this guy, so I get this from 0 to n minus 1. So this is greater than, so since f of xn star is the smallest, so this sum will be bigger than the sum from n equal to 0 to n minus 1, or sorry, k equal to 0, of f of xn star minus f star. But now all these guys are the same, so there's n of them, right? So this is equal to n times f star minus f star. So again, to remind you what we did in lecture 7. What in lecture 7, what we had was actually we had an n plus 1. It's a different. I went up to n here, but basically here, because all of these f of xk's are larger, then this summation was bigger than this. And here in our proof now, we have replaced this xn by xn star. Okay. All right. So now let's do that. To the left-hand side, when you sum them up, you sum it up, you get something that's small, that's bigger than this. Right. So if I sum this, so I can replace this by n times f of xn star, and so I get that that's less than or equal to xk. So that well, I just basically let's copy and paste from here. Take this guy. Plug it, plop it down here. Okay, so all right, so I have that. So when I sum that, now I have the telescopic sum. So the first two terms in the summation things will cancel out in the middle, and I'll be left with this x0 minus x star here and xn minus x star for this term. Okay, so I get x0 minus x star squared minus xn minus x star squared plus then this alpha squared a squared is common to all those terms in the summation, so I'll get n times alpha squared a squared and then divided by 12. All right, so now if I divide by n and take f star to the right hand side, I get that this is less than f star plus well, if I look at x n minus x star squared, that's something negative, right? So this is negative. So I can upper bound it by removing this term. So all I'll be left with is x0 minus x star squared divided by 2 alpha n. And then I'll be left with this alpha squared divided by 2. So the alpha squared a, so alpha a squared divided by 2, some constant. Right? So slightly different from what we had before in lecture 7. Let's see what happens. What happened in lecture 7 was we had this thing here. Both of these terms were divided by n. So this right hand side, this term actually went to 0 as n goes to infinity. The rate of convergence is 1 over n. Now we have a slight problem in that we have this term that's not going off to 0. Okay, so let's take, if we take n to infinity, the best value of x star, that best candidate for x star that I have up to time n, as n goes to infinity, what will happen is that you know that that value is less than f star, but then there's this positive number that gets added to it. Okay, but all hope is not lost. If alpha can be made small enough, so and n large enough, then so suppose you want to get to within some epsilon, right, of f star, then basically you need to make sure that your n is large enough, right? And of course, the way you would choose n large enough will be based on some estimate of the diameter of your space, how big your space can be. And then you make your alpha small enough, right? Your step space small enough so that you make your best value, best xn star, can be made as close to the minimum as desired, right? So basically, let me write that down. So for alpha small enough and n large enough, f of xn star can be made as close to f star as desired. Okay, which is just not as strong as the result we had when gradients exist. So when gradients exist, then all we needed was to make sure that alpha was between 0 and 2 over L. Okay, and as long as we did that, then we had convergence to x star at rate 1 over n. Okay. Everyone see that difference? Okay, so is there something else we can do to guarantee that we actually converge to F star when we use subgradients? Here, I somehow restricted myself to using a constant step size. So could I have done something else other than constant step size?
Non-constant step size.
Yeah, exactly. So don't use a constant step size. So what we're going to explore on Thursday is what happens if I allow the step size to go to 0 as k goes to infinity and at some rate. Okay, and you can imagine that in that case I might be able to get to actually get to the minimum. But because when I start to decrease the step size as k becomes large, the convergence will also get slower. So I have to be careful about how I choose that step size. Okay, and so we'll talk about that. What are some rates at which you can make the step size go to 0 so that you have reasonable convergence rate for your function.
Can we pick the smallest magnitude subgradient at each step to guarantee convergence?
No, the smallest magnitude subgradient. No, that is that's not necessary. Well, so it will slow down, right? As you smallest magnitude. What does that mean? Yeah, you have to be careful. The smallest magnitude, not necessarily the best choice, because then when you're far away, then you're not going to be necessarily, going fast enough down towards the minimum. So,
okay.
So there's a bit of a trade-off.
Yeah.
Right? The smallest magnitude may not be necessarily the best choice. But varying the step size is definitely one way to guarantee convergence. All right. So yeah, we'll talk about that on Thursday. Okay. So, but as far as the midterm goes, it's what I really need you to understand is just the definition of a subgradient. Okay. So the subgradient descent algorithms are really special topics that just bonus things that I have some time to cover now that I've done most of the material I'm supposed to cover for 490. So we'll talk about that on Thursday, and then next Tuesday we'll have a review session for the exam. Okay, and to repeat the answer to the question that I gave on Piazza, the material for exam 2 will be everything that we cover until I guess today's lecture. Thursday will basically be talking about topics that will I didn't test you on in the homework anyway, so it's bonus stuff, extra stuff. So any other questions about the exam? I'm going to make it open notes, but just open your class notes, your handwritten notes, and the notes that I give out, and not any of your textbooks and stuff like that, because some of you don't really have hard copies of the textbook, so it wouldn't be fair. So just the notes. That's all. And it's still going to be a lot more than you had if you had only one or two sheets of things to consult. Yeah. Okay. Any other questions? Okay. I'll talk to you guys on Thursday then.